So hi ladies and gentlemen. Today we're going to be solving moles and equations, and this is the past paper worksheet that we have, that I've given you. Now, in order for us to actually understand what's going on, I need to write something. Okay, so ladies, here's the question, which is in the first paper you have. A hydrocarbon is used in bottled gas for cooking and heating. When 10 centimeter cube of hydrocarbon is burned in 70 centimeter cube of oxygen, the final gaseous volumes were measured. The final gaseous volumes were found to contain 30 centimeter cube of carbon dioxide and 20 centimeter cube of unreacted oxygen. All these volumes were measured under identical conditions. And now we need to find the formula. The main concept here is to actually look at the volumes, So let's look at the carbon. So we know that we have CXHY. Sorry for the bad handwriting, but I think that you got used to it by now. And we have oxygen, We have O2, our lovely O2. And we have a product, and that product is CO2. And we also have water because, let me just get that. Okay. This is my first time using this program, so be patient with me. So this is our equation. So just let me write it a little bit cleaner. CXHY, let me get rid of this. Plus, we have oxygen, and it goes to now when we burn something, the usual things that come out are CO2 and H2O, right? Okay, let me just put that in a lovely color. So, what do we know? We know that this one has 10 centimeter cube. We know that oxygen has 70 centimeter cube. And that some oxygen remain. So it's not 70 exactly. It's 70 equals to something plus 20, right? This something is the one that is being consumed, So in this case, what's reacting is not 70. In this case, it would be 50. So we have 50 centimeter cube of O2 reacting. Okay? So I'm just going to wipe this down. You can pose me. I feel so happy I can wipe anything down. Okay, now what we have also is that 20 centimeter cube is being left, but we have 30 centimeter cube of carbon dioxide here and something here, right? It's a volume because it's a liquid. So we don't want to know this. Now, what's so special about gases? Okay, let me just go like this. So I'm just going to remove the question right now. So what's so special about gases is that they can actually use their volumes as a stoichiometry. Because remember that 1 mole of any gas, of any gas occupies 24 decimeter cube, right? It occupies the same space regardless of size. So CO2 at 1 mole would have the same volume as C3H6O7. This is an imaginary compound. But if this compound was a gas, it would occupy the same volume as CO2 under RTP, which is room temperature and pressure, So let me just wipe this down. Okay. So what can we do now? Well, what can we do is very simple. We look at the volumes, and we say, well, this is 1, and this is 5, and this is 3, right? And this is the same as their stoichiometric ratio. What I mean that if we rewrite this equation, okay, so what I mean basically, if we rewrite this equation and we have the CXHY here, and we have O2 here, and we have our lovely CO2 here, okay, then we should go, okay, with 5 O2, and this is this, 1, and this is this, and 3 from here. The stoichiometric ratio is equal to the volume ratio of gases. If they are all measured at the same space. Okay? So we know something. We know the equations that are written here, so let me just rewrite that. So we know that CXHY is reacting with 5 oxygens and producing 3 CO2 and H2O. Okay? And the H2O is liquid. That's why it's not part of our, because liquids have different properties than gases. This is something that you for sure know. Okay, now let's balance the for X and Y. Okay, so first we have to look at the carbon. Okay, where does carbon exist? Carbon exists here, and carbon also exists here. Okay, so the amount of carbon here should equal the amount of carbon here. So in this case, you should have 3 carbons in this side and 3 carbons in this side. So for sure, because there is no stoichiometric value here, what we're talking about is something like this. It should be C3, right? Okay, now we need to find out this, the hydrogens. Now, what we have here is 10 oxygens, because 5 by 2. We have 2 and we have 5 here, the big 5. We have 6 oxygens here, because we have 3 and we have 2, so they are 6 oxygens. And we also have some oxygens here. So the oxygens are not the same. There are 10 on this side. Okay, I'm just gonna make a new one. Okay, so we know that there's 3C3Hy plus oxygen. That is 5, okay? And it goes to 3 CO2 plus H2O. Remember that the numbers, the big ones, we got them from the volumes, okay? So now we have this, that is 10 oxygens. And we have here 6 oxygens, and we have here 1 oxygen. So they should be equal. In this case, 7 is not equal to 10, right? So what we should do is actually do an equilibrium. So we have 10 oxygens here, 6 oxygens here, so there are 4 remaining here, right? This big 4 here is for oxygen. Now notice that we are just balancing our equation, but we are also looking for the hydrogen and Y. So why did we do this? Well, in CO2 there are no hydrogens, right? There's nothing. Okay, I say right a lot. That was a bad thought. Okay, so there's nothing here that indicates hydrogens are being released. The only way to know how much hydrogen we have is by using H2O, because we only have 2 products and one of them has hydrogen. So in this case, hydrogen is equal to 8, because we have here a very balanced equation for oxygen, where oxygens are 10 and they are equal to 10 here. So, woohoo, we got our balanced equation. So if we got balanced equations for O's, and if we got balanced equation for carbon, then definitely we have a balanced equation for hydrogens. That's why hydrogen is an 8. Thank you very much for listening. See you next time.